Hi, my name is Frank van Overwalle, and I'm going to talk about the role of the cerebellum in reconstructing and predicting social action sequences. This is a somewhat newly discovered function of the cerebellum, the social cerebellum. And I begin with a picture of my hometown, Ghent, in Belgium, and as you can see, this is a typical medieval city center, very nice, as a postcard, and you also see pictures of Belgian fries, Belgian good beers, and so on and so on. Everything you expect from a European city. So it tells you a lot of cliches about tourism. And my point is that the cerebellum actually also works like this. It builds up cliches, routines, automatisms, and so helps us in executing behaviors much more quickly and automatically. Cerebellum serves to prediction. The primary role of the cerebellum is to support sequence learning, the sequences of our emotions or non-motion related cognitions, emotions and so on, to acquire that and to help in predicting future action sequences. That's its main role. So when we intend to execute an action, we have at our disposal a forward model that we have learned earlier, and then we know what to do. And while we execute the behavior and these motor responses, we also have in that model predictions about the external environment, how the external environment should and will react, and the same is true for our bodily sensations. And as soon as we experience some discrepancies in these anticipations, the important thing and evolutionary advantage that we have with the cerebellum is that we can adjust our behavior while we are executing it. So we don't have to wait until the end to say, oh, failure. No, while we execute the behavior on the fly, we can adjust our behaviors. And that's the main advantage of this cerebellar circuit. As I said, this is not only true for own motions, but also for non-motion cognitive social behaviors. So we have in the cerebellum the cellar, so to say, of the brain at the bottom part. We have the interior area, which is mainly involved in own motions and behaviors and sequences of these behaviors. And we have at the more posterior part deals with the motions, behaviors of others and how we understand these behaviors. The cerebellum has an enormous capacity for computation compared to the cortex, the cerebrum. It has 16 billion neurons. The cerebellum has 4 times more, 69 billion neurons. It's a very sexy number. You will never forget this anymore. And in addition, the cortex of the cerebellum and the cortex of the cerebrum are almost the same, the surface. So a lot of computational capacity to encode and all automatizations of own behaviors and the behaviors of others, and even at the level of motions or cognitive elements. Now, the cerebellum, as I said, also has an important social function, and to demonstrate this, autism, which is characterized by impairment in social understanding, shows in this meta-analysis a decreased volume in the cerebellum, the posterior cerebellum. Depression, another meta-analysis, resting state is reduced in the posterior cerebellum. Obsessive compulsive behavior, which is characterized by ongoing thoughts or behaviors that are difficult to stop, increased volume in the cerebellum. So as you can see, the cerebellum is involved in many social behaviors. We are going to focus on some tasks in order to demonstrate indeed that the function of the cerebellum is quite social, and especially we'll focus on one kind of social function which is not related to nonverbal understanding of other people's behaviors, but which is related to mind reading of others' mental state, a higher level of social cognition, which we call mentalizing or theory of mind. And here you can see the 7 networks, major networks of the brain. And in red is indicated the default mode system, of which the mentalizing system takes the most part of it. So we see here on the left the temporal parietal junction, one of the key systems. On the right, the medial prefrontal cortex, another key system. And in the middle here, the precuneus, which is also a very important system, part of the mentalizing network. We have this same 7 networks in the cerebellum, as you can see, and in the cerebellum there is a primary representation on top, a secondary representation at the bottom, and there is even a third one. And we will focus on the posterior cerebellum, where the mentalizing system is located. So we're going to test the social cerebellum, and our task or our goal is to demonstrate the role of the cerebellum in social mentalizing, and especially we'll focus on the posterior cerebellum, also known as the parts crus 1 and crus 2. How do we test it? Well, we developed a number of novel tasks that involve social mentalizing, of course, because that's the thing we want to study. So social mentalizing is about other people's beliefs, traits, goals, and so on. In addition, with some sequencing of these social actions on which these mentalizing inferences are based. For example, sequencing is triggered by asking participants to memorize the order of the actions, or by putting the actions in the correct chronological order, and so on. And we will compare these tasks with the number of control conditions, such as non-social inferences about objects and how they behave. For example, when they are light, they are floating in the air. When they're heavy, they are not doing this, and so on. And non-sequencing conditions, for example, where participants only have to select a number of actions without memorizing the correct order in which they appeared. So I will illustrate this with one of the oldest tasks that already existed, a picture sequencing task. And I will show you the correct order of a mechanical condition. For example, here you see, it's more or less like a movie where you see the car bumping on some rocks that then fall on a tree, and the tree cracks and falls down. It's like a movie. We can easily understand the right order. Another one is a social routine. You go to the shop, pick your items, say hello, and then leave the shop. Very easy to solve, it seems. What about this one? I'll give you the numbers of these 4 pictures and ask you, how would you put them in the correct order? I give you a few seconds to do that. It's not that easy because it involves a false belief, and a false belief is the same as an outdated belief of the boy. So the boy, it begins with number 2. The boy sees that he still has some chocolates in his box, then goes playing, while the girl takes his chocolates, eats them, so that the boy is very surprised to come back and see that they are gone. What is important here is that the boy has an outdated belief of reality. We see reality, the most recent version of it, the boy doesn't. And so he has a false or outdated belief. And making the distinction between what we observe as reality and what he believes is reality, making that distinction is important to understand the mental state of other people, or to mentalize. As you can see here in this study, we compared the behavior on this picture test between healthy controls and cerebellar patients. And as you can see on the mechanical items, they did quite well. The social script, they did very well. But in the false belief script, they really did much worse. So the combination of sequencing and false beliefs, that combination was detrimental for cerebellar patients. We extended this task with a true belief task. You see here the false belief task. We extended it with a true belief task, which was almost the same, but simply a story where the boy calls the others to join him eating the chocolates. So there's no outdated belief. And then we investigated this picture test and also verbal version of it under the scanner. And we found that picture sequencing indeed activated the posterior cerebellum compared to the mechanical, both for the false belief and the true belief, showed stronger activation at the posterior cerebellum than the mechanical conditions. This was true for the picture sequencing as well as for the verbal sequencing condition. So where a number of sentences were given rather than pictures. Okay, this was the first attempt to show that the cerebellum was involved in sequencing of social actions. What other social mentalizing activities and inferences could be involved? So we developed a number of novel tasks. One of the tasks was, is this person a liar or not? We provided participants with a number of sentences that were related to lying, honesty, or not, and they had to memorize these sentences in the correct order. So this was one of the sentences, as you can see here. And after reading all of these sentences, the conclusion is that she is honest. But they also had to memorize the order. That's one of the tasks. Another one is in which we developed a number of goal-directed trajectories. Like this, we had a number of agents, as you can see, the blue Smurfs. These are the little Belgian heroes, and they pursue a number of goals, and each of these Smurfs has a preference for one of the goals. And we asked the participants to learn what their preference was, and also to memorize the trajectory that they took. Okay, I'll give you an example of this. Here we see Papa Smurf moving, avoiding obstacles here, and then moving towards money, flowers, cake. What does he really prefer? He goes to the cake. Oh yeah, we now know what he likes. That's another task. And still another task is where we learned implicit sequences. So far, all the sequences had to be memorized or replicated explicitly. We wondered to what extent the cerebellum also can learn sequences, belief-related sequences implicitly, because actually the cerebellum is involved in automation, which often involves a lot of implicit learning. So here we have a task again with our two heroes, little blue heroes, and these two little heroes looked at the screen and could see how many flowers were offered to them, either to Papa Smurf or to Smurfette. But sometimes they turned away from the screen, so they couldn't see how many flowers were given, and still had the outdated belief that the number of flowers was still the same as before, so the false belief. I'll walk you through the task to see how to demonstrate you how this worked. In reality, it's of course much faster, but I will go slowly with you. So he sees 1, correct answer is 1. Still 1, he hasn't seen anything has changed. She thinks it's 2, still 2, still 1, and so on and so on and so on. And this is repeated many, many times. And importantly, without participants knowing, there was a standard sequence of true or false sequences that was always repeated. So this is a kind of serial response time task. And as you can see, over time, they implicitly learned this sequence without much awareness and became faster at it, as you can see here. And more importantly, compared to the standard sequence, when we all of a sudden introduced a random sequence, the response times went up again, indicating that indeed they had learned the standard repeated sequence. Now, of all these tasks, is the posterior cerebellum involved? In the trait-implying task where they had to memorize the actions, yes, you can see this. In the goal-directed trajectory task, again, yes, the posterior cerebellum was involved. And for the implicit belief sequences, again, the posterior cerebellum was involved. So in all these three tasks, in the social condition compared to the non-social condition or the non-sequencing condition, the posterior cerebellum was involved as predicted. Now, we had a number of following up tasks that were quite of interest. For example, imagine now that this person is lying or not lying, and that there are some inconsistencies. So, for example, we tell about Lixia, the same task where they have to memorize the order of these 6 unrelated actions, but related to the same trait or not. Lixia tells testimony, friend the truth, confession, does nothing, tells a lie. Oh my God, something is wrong with her. There goes her reputation as being an honest person. So how does the cerebellum deals with this kinds of inconsistencies? What we found was that when we compare the honest individual versus the lying individual, or the honest trait-implying actions versus the lying dishonest implying actions, then we saw stronger activation of the posterior cerebellum, indicating that the posterior cerebellum also takes into account the social implications of these actions. Because if the posterior cerebellum would have only encoded the sequence by itself, then it would not show any difference. But the cerebellum also encodes the social implications of this, making, in some sense, the cerebellum a true social cerebellum. Another interesting study is the following. Imagine this situation where you see riots, and then we would ask you, what do you think that will happen? Would you think there would be a lot of violence and so on? And all of a sudden you learn this. Clearly, this doesn't fit with your expectations. And I believe it's also photoshopped. But it shows that sometimes we can be surprised in our predictions and make wrong predictions about information from the past on the future. So that was the task involved. We provided participants with 6 sentences. We told them Furmak is a dishonest person. They knew it in advance. Then we gave them 6 sentences. By the way, in all of these stories, it was not always about dishonesty and honesty. It was about other traits as well. But I give you examples of this one. So dishonest, and they had to select the 4 actions that fitted with being dishonest. 2 that were not fitting had to be dropped, and then they had to put these actions in the correct chronological order, which was always possible to have one correct order. And again, what we saw is that when people were making predictions about actions that were consistent with information about this person, the posterior cerebellum was involved. So making also clear that the posterior cerebellum is not only involved in understanding sequences of social actions, but also in making predictions about subsequent future actions that are of a social nature. And as a final step, I want to show you some results of a study in our lab on brain stimulation. We stimulated the cerebellum with TMS, transcranial magnetic stimulation, as shown here. And we again used the picture sequencing task to see whether there was any improvement before and after that stimulation with healthy participants. Okay, here you see the results of the different types of items that we provided to the participants. And here is the duration, so the response times before TMS. This is after TMS. And as you can see, they're all shorter. Now, if we make a significance test, then you can see that these differences are all very significant. And if we compare this with the sham condition, none of the sham conditions was significant. So there was really a learning effect in the sense that they became quicker at this picture sequencing test. under TMS after stimulation, but not under fake stimulation, a sham condition. This was in the picture sequencing tests. For the verbal sequencing test, the results were not neat, as you can see here. That is before stimulation. After stimulation, they were quicker. Most of the time, this was significant. But as you can see also in the sham condition, indicated by the red asterisk, there was also some effect. So here the effect is not so robust. But anyhow, overall, you can see that stimulation of the posterior cerebellum is helping to increase the time to make people faster in resolving these questions, not only for social true and false beliefs, but also for other items, because of course, TMS is influencing not only the posterior cerebellum, but a major part of the cerebellum. So we expected to have improvements across all items. And this is all just to end that these series of studies have shown that the cerebellum is important for predicting social action sequencing. So the non-motor social cerebellum is part of a predictive coding system that deserves more attention in neuroscience, as is it especially important in understanding the computational architecture of perception, action, and choice behavior, according to Friston, which is the major author of the predictive coding approach to the brain. And I thank you for your attention. I also thank my collaborators and funding agencies, which are listed here. And I'm ready to answer any questions you have so far. Thank you.